some trend we can identify if you look at the human history and human attempts to understand the universe. The one trend we could think of is that it never turned out the way we wanted it to be. And
20th century physics, there's still some things that we don't have the formalism to calculate. Is that it turns out for black holes, CE black hole is equal to CV black hole is equal to 0. From the perspective of particle physics, this is an incredible fine-tuning, because particle physics tells you that, which in turn is just proportional to the imaginary part of the Feynman propagator of the time-warp product of two Q's. But the optical, the matching. This one here.
Right.
So classical observables depend only on G retarded, and G retarded of omega looks like an integral of A plus over omega prime minus A minus.
I have one more question. So this question is a bit of a preface. The last week, an interview between a science journalist and Dr. Svetlana Vergundiga, and a world leader in exoplanetary and astrobiological research, surfaced in which the journalist presents a series of questions about classical physics and planetary science, which she, despite her unrivaled expertise in the field, did not answer even to her own satisfaction. The interview ended with her becoming a little discourteous and even stage denial. So the question is, given the popular heliocentric model, what experiments do you know of that evidence that the Earth is currently moving at an average speed of 66,000 miles per hour, or Mach 88 in an elliptical orbit around the sun, or spinning at an almost twice the speed of sound, or moving in any way at all consistent with the proclamations of the widely accepted heliocentric model?
I'm not an astronomer.
Would that be a no? You don't know any?
Me personally?
Yes.
I'm not an astronomer.
Is that a no? Okay. So the last one, the third one, I guess, in the interest of everyone's time.
Okay.
Can you think of any experimental demonstrations of gas pressure without a container, or adjacent to a vacuum without a solid barrier?
So I'm not a statistical.
Are you a physicist?
Marginally.
Okay.
I'm on board.
Can you think of any experiments today that we can do today that distinguish gravity as a force as distinct from the effects of density and buoyancy and fluid medium?
So I'm not a fluid mechanics,
Physicist stuff.
Maybe, I don't know. You have to ask my advisor.
This is the physics department.
I think you can ask the crowd.
A physicist doesn't have to know.
It doesn't have to. I just wanted to see if you knew anything.
Because it's very specialized question that you're asking. You should go to, very specific.
She retarded.
Sorry, I cannot stay in a neutral biological form. They have to be in an ionized form, and then. It would be the same particle effectively.
Mr. Vachaspati, or Dr.
Yes.
Vachaspati, he's recommended. So I've come to 2 or 3 of these cosmology colloquiums,
Yeah.
and I've asked these 2 questions, and he's recommended that I ask the cosmologist these questions because
Okay.
the physicist prior could not answer them.
Okay.
The first question is, and this is perfect because you do tests of gravity.
Yeah.
What experiment have you come up with that, or have you discovered or seen that evidences the existence of a force called gravity, which as distinct from the effects of density and buoyancy in a medium?
What evidence there is for gravity?
In the experimental, as distinct from the effects of density and buoyancy in a medium.
The fact that planets move around, lots of evidence.
So I meant experimental evidence. So
That's experiment.
what's the independent variable in that experiment?
Okay, I guess you could look at different
Or control.
samples. I mean, you can drop things in a vacuum,
So things are more dense than zero. I mean, so a vacuum is, there's a zero medium, so everything's
You can
equally
drop
more dense.
Objects.
As
You just
distinct-
take a room,
Yeah, yeah, yeah.
evacuate the air, and drop
Right.
things, and then they all fall the same.
Equally more dense than nothing, right? They're both equally, so it's distinct from the effects of density and buoyancy.
Yeah.
So gravity is a force that's
Yes.
it has nothing to do with density and buoyancy, right?
Yes.
It exists there whether or not.
Yes,
right.
it's
So when
the-
things fall in a medium,
Yes.
it's because they're equally more dense than nothing. In a vacuum, they're equally more dense than nothing. That's why they fall at the same rate. So the question is more as distinct from the effects of density and buoyancy.
Yeah.
If the answer, if no, that's fine too.
I'm not sure I can add more than I said.
Then the second question
Yeah.
is, so your cosmology depends upon, so the second law of thermodynamics stipulates that you can't have a gas pressure system in the midst of a vacuum. Like a high pressure always goes to low pressure.
Yes, that's true.
So has it been brought up within the field of cosmology that the heliocentric cosmology depends upon a violation of the second law of thermodynamics?
What
in
is
order
a
to-
heliocentric? Is it
The heliocentric model being
centered around the Earth?
heliocentric means, or let's say the cosmological model assumed within the parameters of the general relativity theory, whatever you decide is the center of the universe. But normally you have gas composed stars in the middle of a vacuum. So
Yeah, so yes, you're right. So if you have gas, it would
Right.
expand into the vacuum, absolutely.
So do you know of any demonstrations of gas pressure in the middle of a vacuum without a solid barrier between the two?
No.
So would it be true to say that the cosmological model that underpins the assumptions of the popular cosmology, whatever it is, depends upon a violation of the second law of thermodynamics, which is
No,
not
because
demonstrable?
there is no, it's not like we're putting, first the universe doesn't have a center,
Well,
it's
yeah,
infinite.
sure. Whether center or not.
and it's uniformly filled with radiation. So it's already equilibrated, so the gas has distributed itself throughout all of the volume of the universe.
Okay, so is that possible to demonstrate, let's say, gas pressure adjacent to a vacuum without a barrier between the two? Is that demonstrable in any way?
I'm not sure
Let's say I have a
understand the meaning.
let's say I have a pressurized shoebox inside of a vacuum. I poke a hole inside that shoebox. Is there any way to demonstrate air not going into the vacuum and staying inside the box, as opposed to?
I don't think so. As you, I think you're absolutely right. If you poke a hole, it will go out. I know. I can't think of unless you just put the shoe inside a very dense, much denser gas or something like
but
that,
would-
or
that
put
would
it
not be
inside
vacuum, right?
like water or something. I don't know.
So it's true to say you can't have gas pressure in the midst of a vacuum without a solid container.
Yes,
Okay, so how is it the case that we have atmosphere on Earth without a solid container?
because it's attracted to the Earth.
Via gravity,
By
right?
the gravity.
But why doesn't gravity hold air in the shoebox?
Because the shoe doesn't have enough gravity.
The Earth presumably does.
Earth has a lot of gravity.
The Earth
and
is
shoe
inside.
and the shoe doesn't.
So why doesn't Earth's gravity hold the air inside the box?
Because, sorry,
Why doesn't Earth's gravity hold the air inside of the shoebox, which is in the midst of a vacuum?
because the gas has pressure. So it has pressure and it just.
It just goes out into the
Yeah.
vacuum.
Sorry,
I'm just saying.
I have people waiting and I need to go.
Got it, all right.
You think supermassive black?
So there you have it. Now you know what happens when you take basic flat Earth and thermodynamic and cosmological questions to top physicists and astrophysicists and cosmologists at various universities, whether they be that of Carnegie Mellon University in the case of Ira A. Rothstein, or in the case of Simon Fraser University, which is the home of Dr. Pagosian, a specialist in cosmological tests for gravity. When asked questions of the kind which should be very simple to answer, pertaining to gravity and gas pressure in a vacuum, professors of this high status either resort to snark, evasion, or are simply flabbergasted